Welcome to This Explainer. Today, we are diving deep into how AI models like BERT learn to genuinely understand human language. We're going to unpack the true power of surrounding context and discover exactly how an AI learns to read between the lines. All right, let's jump right in.
Masked, I go forward. That is a quote from the philosopher René Descartes. Now, he probably wasn't thinking about neural networks when he wrote that, but it is literally the perfect philosophy for how some of today's most powerful text analysis AI models actually work.
Here's our roadmap for today. We'll cover reading in both directions, the fill-in-the-blank test, contextual embeddings, and finally, fine-tuning for specific tasks.
Okay, part 1. Reading in both directions, the shift from causal to contextual.
To really get this, we have to look at how AI physically scans text. Older models were strictly left to right. They processed words sequentially, trying to predict the next word without ever peeking ahead. Think of it like reading through a tiny peephole. But bidirectional models, total game changer. They look at the entire sequence of text simultaneously, left, right, the whole shebang. By doing this, they create these deeply contextualized representations of every single word.
And because they look at everything all at once, these masked language models are what we call encoder-only beasts. So they aren't built to be conversationalists. You wouldn't use one to write a high school essay for you. Instead, they are highly specialized readers, labelers, and interpreters of text.
Moving on to part 2, the fill-in-the-blank test, or training without predicting the future.
So here's the catch. Since a bidirectional model already sees the entire sentence, you can't train it by asking it to predict the next word. The answer is literally right there. Researchers had to invent a completely new game. They borrowed a concept you probably remember from grade school, the classic fill-in-the-blank test. In linguistics, this is formally called a closed task. You take a sentence, hide a word, and ask the model to guess the missing piece based entirely on the surrounding context.
Now, this falls under a broader machine learning category called denoising. Imagine deliberately messing up your training text, corrupting it with noise, by masking words, swapping them out, or just straight up deleting them. The AI's only job: fix the text. It has to recover the original input using absolutely nothing but context clues.
Check out the statistical genius behind this training. In models like BERT, they manipulate about 15% of the words. But they don't just blank them all out. Nope. 80% become a special mask token. 10% get replaced with a completely random, wrong word. And that final 10% just left completely unchanged. Now, why on earth would they do that? Well, out in the real world, the model is never going to see a mask token. So this clever 80-10-10 split keeps the AI constantly on its toes, forcing it to intensely scrutinize the context of literally every single word.
All right, part 3. Contextual embeddings and meaning, solving the problem of ambiguity.
So how does this training build a profound mathematical understanding of language? Well, it tackles the biggest headache in human communication. Our language is highly polysemous. That's just a fancy way of saying our words are loaded with overlapping, ambiguous meanings. A single word can signpost vastly different concepts depending entirely on how it's used. Take the word bank, for example. If I just blurt out the word bank out of nowhere, you'd have no idea what I meant, right? Surrounding context is absolutely crucial. It's the only way to know if we're discussing a financial institution holding investments or if we're talking about a muddy, sloping mound of earth right by a river. Or think about the word die. Depending on its neighbors, it could be the tragic act of passing away, it could be a singular piece from a pair of dice, or if the model happens to be reading multilingual text, it could just be a super common grammatical article in German. Older language models really struggled with this. They just assign one static mathematical value to a word, no matter the context. But because our masked language model reads bidirectionally, it creates what we call contextual embeddings. Basically, a word's mathematical identity dynamically shifts based on the company it keeps. The mathematical vector for bank in a finance sentence gets pushed far away from the vector for bank in a river sentence. It creates these distinct, beautiful clusters of meaning in a high-dimensional space.
Let's bring it all together in part 4. Fine-tuning for specific tasks, turning a general reader into a specialist.
Once the AI has developed this super rich, context-aware reading comprehension, we can actually give it a real-world job. We do this through a pipeline called fine-tuning. Basically, we take our massive pre-trained model, the one that spent weeks playing fill-in-the-blank, and we stick a tiny piece of specialized circuitry on top called a classifier head.
We freeze the massive base model and just train that new little head on a smaller set of labeled data so it can perform a specific downstream task.
Now, if we want to classify an entire sequence, say doing sentiment analysis on a movie review, we use a pretty clever trick. We insert a special CLS token right at the very start of the sentence. As the model processes everything bidirectionally, this token acts like an anchor. Its final mathematical output ends up representing the model's view of the entire sequence. Then, we literally just feed that single vector into our classifier head to get our positive or negative label.
But what if we want the model to act more like a laser-focused highlighter? Say we wanted to analyze the text word by word to spot specific proper nouns. That is a sequence labeling task called Named Entity Recognition, or NER. We're asking the model to comb through and tag every person, location, or organization it finds.
Check out how this breaks down using the standard BIO tagging system. That stands for beginning, inside, and outside. Take the phrase Jane Villanueva of United. The model learns to meticulously label Jane as the beginning of a person entity, Villanueva as the inside of that same entity, the word of as outside any entity, and United as the beginning of an organization. Token by token, it maps precise meaning onto every single word.
So we've seen how these models scan the whole context, learn by denoising, untangle deep ambiguities, and get fine-tuned to extract incredibly precise data. Which leaves us with this final, kind of provocative thought to ponder. If an AI builds its entire foundational understanding of human language simply by playing a masked game of predicting missing words, does it truly comprehend meaning the way we do? Or has it just mastered the world's most insanely complex, high-dimensional game of context clues? It's a fascinating question to chew on. Thanks so much for joining me for this explainer, and keep learning.